So I want to start with showing you a simulation of which is the demonstration of uh, our theorem which we have been using, that if you pick a sample of large enough size from any distribution, you have a distribution where some quantity is distributed according to any probability. If you pick a sample and sample is large enough and compute the mean, this mean is a random number, but is distributed according to, it will be distributed according to the normal distribution. And the mean of this normal distribution would be same as the mean of the original distribution, which was not necessarily normal. And the standard deviation would be reduced by a factor of square root of n, where n is the size of the sample. So let me see if I can so what I have over here is, so I have some data which is listed over here. It's just a list of numbers from 50 to 60. And I'm assuming that these are the values in my population and they are distributed normally. So I can draw its probability distribution graph, which you can see on the screen. So these values are there and each one of them is equally likely. Now I can pick some samples from this. So if I pick a sample of size 4, I get some number like 58, 57, 53, 60. It's a random sample. Next time I pick, I get some different numbers. Every time I get different numbers. So when I pick a sample, I can compute its means, which I have computed this function. You don't need to worry about it. I'm just going to show you that every time you pick a sample, you get a different mean. So I'm picking samples of size 4. And every time I pick, so this time I got a mean 52.5, next time 56, 51. So every time you are getting a new mean. By the way, the mean of my original sample, original population is 55. You can compute it that if you just add all these numbers, divide by 11, there are 11 members, you get a mean of 55. So
why are you getting different means?
because means are, remember, the mean of sample mean is a random variable. Every time you pick a sample, you get a different mean. That's what is you are seeing over here. Somewhere close to 55. So this time I hit very close, 55.25. But every time you'll get a different number. So I can collect many of them. I want to make a probability distribution. So I'll collect about, let's say, 10,000 of them and then plot them. And I pick a sample size of 4. And when I pick 10,000 of them, I'm essentially plotting their probability distribution. So you see that I started with a distribution which was uniform. And I picked a sample of 4. I get all these numbers, all these various numbers, but they are distributed around the same central value. And every time I plot, I get something slightly different, but looks very much like a normal distribution. And if I pick a sample of size 2, it still looks very normal, but probably a bit more like triangular, close to normal, but it's not getting normal. But as soon as I'm hitting 5, it looks very much like normal. These are samples of size 5, their probability distributions. But if I pick bigger samples, let's say 25, size of 10, let's start with 10. Then it looks more and more like the normal distribution. And you can check one more thing. So let's say I pick a sample of size 3. Is distributed, you can see that it touches the boundaries between 50 and 60. It's spread more. But when I increase the sample size, let's say to 10, the spread has reduced. It's like confined to these values 52 and 58. And if I increase the sample size even more, let's say 25, then the spread has decreased even more and looks very well like a, maybe I should increase these, very much like a normal.
Sorry, 100K?
You don't need to worry. This is just the bin size, how I'm plotting. This is just about how I plot. So in how many divisions I divide these numbers, because the mean, when you calculate, it becomes it involves decimals. Even though I started with integers, but when you compute the means, they become decimals. So just to capture that, I have uh, putting various, so I'm plotting this into bins of 50 bins. That's all it means, nothing more. And you can check the mean of a sample. If I pick a sample, let's say of size 4, and my answer is 55. So the mean of the mean is exactly what I was expecting. It's the original mean. And I can change the sample size. It doesn't affect it. It remains very close to 55. Since I'm computing a probability distribution in a fake way by collecting 10,000 samples, that's why it's slightly off. But if I increase this accuracy of my probability computation, it becomes even more close to 55. It takes the computer a little bit more time, but doesn't depend on this sample size. Always gets 55. On the other hand, if I compute the standard deviation, which you could see in the graphs as well. So if I first pick a sample of size 2, this second variable is the sample size, I get a standard deviation of 2.2. By the way, the standard deviation of the original data is 3.3. So picking a sample of size 2, it gets reduced slightly. But if I pick a sample of size 4, it's smaller. and keeps getting smaller. So this standard distribution, the standard deviation of the sample means it gets reduced as you increase the sample size. Now let me pick another data. So this time I have only these 4 numbers. So if I plot this is its probability distribution. This is a new population, and in this population you have only elements which have values 51 and 52, 59 and 60, and they are all equally probable, all these 4. All other values have 0 probability. So this distribution is not uniform. It has 2 peaks at 2 places, but the mean is still 55. It's very close, 55.5, but they're distributed very differently. Now if I now I pick samples from this population and pick samples of size 2 and plot them, you get something like that. It tends to be going towards looking like a normal distribution, but not really. It has these 3 peaks, which are reminiscent of that nature of the original data, that it had peaks at the 2 boundaries. But the mean of this is still same as the original population, 55.5, because that theorem had nothing to do with the fact that if you get the distribution as normal distribution or not. But now let's see what happens when I increase the size of the samples. Now I start picking samples of size 4, and it starts looking more like a normal. Let me increase it to 25. Becomes almost like a normal. And this is exactly like a normal. So by the time I have reached 50, although my original data that had very different distribution, but by the time I'm picking samples of 50, the means of those samples have a distribution which is a normal distribution. I can just list for you. Let me show you one more data. Let's say so this is like a triangular distribution, but probably closer to a normal distribution. So when I'll pick the samples from this, they will start looking normal more quickly. So if your original distribution is normal, any size sample gives you normal. If your original distribution is not normal, then you have to increase the number of size of the sample to get closer to the normal distribution for your sample means. So here, even 2 is giving me pretty much something like a normal distribution. And by 10, it's exactly normal. And you can see this phenomena here as well, that it remains normal starting from 2, but at 2 is spread out. It's spread out between 50 and 60. When I increase the sample size, this starts becoming tighter. and at, let's say, 100, 155, is extremely tight. So as you increase the sample size, the distribution becomes narrow. Let's look at this data. Z4, I had called it. So it's just very random data. But it doesn't matter. By the time you are picking a certain number, a high number of samples, let's start with 2. Not really normal. At 5 starts looking normal. So that's essentially, you are over here seeing the demonstration that when you pick samples from any kind of distribution, doesn't matter, but if you pick a large enough number, then your distributions of the sample mean, they will always follow the normal distribution. And if the original data looks more like normal, then this happens earlier. If your original data is very skewed, then you will have to wait. You will have to pick larger sample sizes. But if it's uniform, we saw that even for uniform, it got normal very quickly at 15, around 10 or 15. So unless you have skewness and very squiggly data, you become normal very, very quickly. And for real world problems, real world applications, the data is not usually that much jumbled up at places and empty at other places. The probability distributions are not of that form usually. So for all practical purposes, by the time you go to 25, you have normal. Actually, like you saw over here, I'm only picking 10 samples and it still looks very much like a normal distribution. So any question? And yeah,
y-axis में I noticed कि probability 2 तक जा रही थी. Why is that so?
यहाँ पे
ये graph में
ये
y 2 तक जा रही थी.
ये right now the probability, the maximum probability is at 0.4.
हाँ, लेकिन ऊपर जब आप हिस्टोग्राम बना रहे थे तो एक दो ग्राफ्स में 2 तक जा रही थी.
Oh, that was just because how I had chosen the data. See, for example, if I pick this, I have certain numbers. The only thing is, like, the sum of these probabilities have to be 1. So I'm just picking them this way. Or if I pick this, then they have to like over here, it's just that the total sum of the probability should add to 1. I think there is a factor of 2 problem here, because these, yeah, the way I'm using a function within R which was bringing it down to some distribution which you can plot with within a range of 1. So I think it's off by a factor of 2, which I can see over here. Each one of them should give you 0.25. It's giving you 0.5. Yeah, I think there's a binning problem. It's binning in computing these numbers, it's binning them together. So don't look at these numbers. Just forget about these numbers and think of them as relative probabilities. So these are probabilities over here, and forget about this scaling over here. So just relative probabilities among them. This is equally probable. Over here, these are just relative probabilities. This central value is more probable, they are less probable, and so on. So any other question? Let me, I'll actually, I'm doing it in the console, but all of this are programming you can do on web pages, for example. That is called uh, the Jupyter notebooks. You can just open Google Chrome web page and you can do all of this over there. I'll write this code in Jupyter and send a link so you can play with it if you want. So let me just switch back and I'll be connecting back. I'll be online, but I'll mute my mic for 2 minutes, then I'll be back. Okay, so after this demonstration, let's continue with some more examples which we were doing last time. Let me just write some formulas clearly. So first of all, you have this, that if you are computing the probability of a normally distributed variable to lie between two values, then this is same as the probability of the standard normal to lie between two of its own values, where you compute this ZE or ZB through this. That's the relation. So for example, if I want to know that what is the probability of X being between its 2 sigma, 2 standard deviations around its mean value. So you have this distribution, this is X bar, and over here you have somewhere, well, probably here, 2 sigma. So you are asking this probability. So if I compare over here, so Z, if X is X bar plus 2 sigma over X bar plus 2 sigma, I have to include this from the formula over sigma. So this is 2. And we know, so the upper limit is this, lower limit is, this is when X bar plus 2 sigma, this is when X bar is X minus 2 sigma. This will give you minus 2. So that means that the standard normal would be between minus 2 and plus 2, because we know that the standard deviation of the standard normal is 1. So these probabilities directly correspond. So if you know what is the probability to be within, let's say, 1 standard deviation of the standard normal, it would be same for any normal to be within one standard deviation of its own probability distribution. And you can also probably write this formula, that if you want to know this probability for x to be between two values, usually you will compute by computing these two numbers of x being greater than, well, let me write it more carefully. So you want this. This is xb and this is xa. You want this area. So you compute the area probability of x being less than xb and subtract from it the probability of x being less than xa, this area. That gives you this middle area which you want. So you can use this formula to compute the probabilities between two numbers, because these things are usually given to you. So these things you can easily compute, look up in the table, or get it from an online calculator. Now, let's take an example, and it will also introduce another concept. So this is your problem, and it introduces a new concept called acceptance level. It's not very new, it's just a use of this center limit theorem, that we expect the means of samples to be following a normal probability distribution. So suppose you have there's an insurance firm and there are insurance claims, and they have their whole database of insurance claims. They know that the mean of the insurance claims is 6,000. Let's say $6,000, and the standard deviation in their data is $2,000. And insurance claims are usually not normally distributed. There are some which are very high, and most of them. So usually you expect, if these are the claim amount, that you have some flat curve. You have some flat curve and some tail over here. And then maybe some small tail here. In any case, whatever the probability distribution is, that's all you know, that the mean of the claims, historical claims, is 6,000, and the standard deviation is 2,000. Now you want to keep an eye that nothing is changing in your claims pattern. Whatever your historical distribution is, that's all you're getting, because your whole model of your business is dependent on how you expect the claims to behave. Now you want to keep a daily eye on this. So suppose you, what you do is you pick every day, or let's say every week, a sample of whatever the new claims you get. You pick a sample of 100, and and then you compute the mean of these claims. You know that it would be normally distributed, around, so this mean is a random variable. It will be distributed around this value, 6,000. But any given day, you don't expect it to be 6,000. It will be jumping around this number. So how could you ever conclude you want to keep an eye that something fundamentally is not changing in your business, or someone is not trying to do some fraud, or the market is not fundamentally changing? So what can you do about it once you get these random numbers? Well, you know what is the standard deviation in these means. You know that you expect it to be sigma over under root n. Sigma in this case is 2000. So this is 2. So you expect the standard deviation to be 200. And we computed last time that the probability of normal, or this is the standard normal, or of any normal, because standard normal is this, then any normal is same within its standard deviation. You know that within 2 standard deviations, the probability is 95%. So a claim being, sorry, the average of claim.
Sir, isn't one standard deviation away from the mean 95%
No,
or 90%?
no, not one standard deviation. One standard deviation is about 60 to 63%. 2 standard deviation is 95%.
Okay, thank you, sir.
So we can do it, for example. Sorry. Remember, this is the integral. So I'm computing it between 2 standard deviations. It's 95. Within 1 standard deviation, it's 68. And 3 covers almost everything. Sorry. Three covers 99.7% of the possibilities.
Sir, is this also called an empirical rule?
Well, it's empirical, it's mathematical. You want to call it empirical, that's okay. Empirical, when people usually say because empirical you say because not all distributions are normal, but for most distribution you expect them to be very close to normal. So that's why people say it's an empirical rule. For any distribution, like if you don't know what's the underlying distribution, you're picking samples like we saw in the central limit theorem, you expect that this quantity to behave close to normal. So then you say that empirically speaking, most of the things should follow this rule. But if you know that the distribution is normal, like in this case, we are picking 100 samples. So there's no reason for this thing to not, our theorem tells us that the means of the samples are going to follow the normal distribution. So it's, in that case, this empirical becomes mathematical. It's like literally true. So yeah, so what I was going to say now, so your average is going to hop, but you know that if it's plus or minus 2 standard deviations, and what's the standard deviation? 200. So 2 standard deviations is 400. So if your average comes out to be, yeah,
2000 लिखा है अपने ऊपर
2000 लिखा है, Yeah, because the standard deviation of the original claims is 2000. But for the samples, the means of the samples, it becomes
Okay. Thank
200. So if your average comes out at, so you can put, for example, a quality control, and this is called the acceptance level. You want to keep an eye that your claims are remaining around the average. But you know it's a random variable. So if you pick a sample of size 100 and compute the mean, you're not gonna get exactly 6,000. You're gonna get something different. So it's up to your tolerance that when you want to trigger that something fishy is going on. So for example, you can put an acceptance level of 95%. That I'm still tolerating, maybe it's just by chance I got. So if you get a number 64,000, you can say I'm within 2 sigma or within 95% of the chance that this can happen. If this goes out of this bin, then you say there was only 5% chance that this could happen. And this may give you, this may be worthwhile now to go and check if something has changed in the market or if someone is trying to put in fake claims or something like that. So you can use this kind of concept, acceptance level, to put quality control on many things.
Sir,
Wait. Here you had acceptance level of 95. Usually you put it in terms of sigmas. You can also say I need an acceptance level of 3 sigma. So if it is within, if my random sampling gives me mean within 3 sigma, maybe I'm still within a chance. But anything going beyond 3 sigma, you should be very suspicious that something fishy is going on. What I expect from the original, what I was expecting from the original population mean and standard deviation, that is not being followed. So either this has changed or this has changed. So your original claim about the population, which was essentially their mean and the standard deviation, has changed. If your sample mean, and remember this time I'm just getting one sample, only one sample, and computing its mean. I know I'm going to get some random number, but if it's beyond 6,400 or less than 5,600, there was only a 5% chance that it could happen. So then you have a probability, that maybe this has changed. So what was the question?
sir, I got clear. Thank you.
Okay. Now this was, so these are called, this sample mean is called, as we were discussing, a statistic. So you pick a sample and compute some quantity out of the sample, and you're trying to guess something about the population using this statistic. You can make other quantities. For example, you can talk about proportions. So you have some test, some binary test or quality for the members. Then you can talk about the proportion. For example, in a population, in a class, how many are females? So for each member in the class, you check, are they female? If they are female, then you pass. If they are not female, then they fail. So then you can compute the proportion. It's just, this is the members that pass the test, and this is the total members. This obviously you can do for a finite population, and if it's a infinite population, then you will have some probability that how many of them pass this test, and that's exactly your proportion. So proportion is when you can talk about a binary variable, yes or no answer. So suppose you have a population and there's some quantity whose proportion you want to know. So there's this P is proportion in the population, and you want to guess it through some sampling. So suppose you pick a sample of size n, then you can use this theorem, and I have decided to not waste time on proving. I have this tendency of going into proofs because of my training, but I'm gonna try to avoid it. If this is true, this is, you can take as a rule of thumb, then this p hat, which is small p hat, which is sample proportion. So you're picking sample. Every time you pick, you have a chance. Your proportion will not be fixed. Your proportion will be a random variable. It will be hopping around. So it will have a probability distribution. And what you know, it's again an application of central limit theorem. Central limit theorem I had defined in terms of the mean, sample mean, but actually you can define it in more general terms, and then it gives you many different results. Sample mean result was one of them, and this is another. It says that this p hat sample proportion becomes a normally distributed random variable. And you can also talk about its mean of the sample proportion. It's a probability distribution. You can compute its probabilistic mean. That is actually equal to the population mean. So it's this kind of variables, this kind of statistic whose average, who become random, but the averages are equal to the population averages. You call them unbiased. So it's an unbiased statistic because its mean is equal to the population proportion. And its variance, which is just the square of the standard deviation for this, is going to be or standard deviation is this. So let's do an example. So suppose it is known that in some standardized exam, maybe some entrance exam, only 70% of students are expected to pass. Or maybe you have the database of whatever number of people take this exam every year, and you know that 70% of students have passed in the database. So if you pick pick a sample of 100 students so what is the probability that 80 students in your sample have passed? So we know that they follow the proportions, sample proportions follow the normal distribution, and we know that the average is 0.7. And this we can compute from the above formula. You have to put P here, which is 0.7, because 70% of them have passed in the population, divided by 100, your sample size. So this turns out to be 0.054. So you have a normal distribution. Normal distribution, I'll come to your question, with, I also use this symbol for the averages. This is same as, this is the central point of that normal distribution, and standard deviation is 0.054. So you have to listen to me carefully. Big P is the population proportion of people who have passed in the population, and small p hat, small p or p hat is the proportion in the sample. They obviously are not going to be same, because sample is just random choice of all those people, and you don't expect them to be exactly same. Now you want the probability that 80 of them have passed. So if 80 pass in the sample, that gives you a proportion 80 out of your total sample size. That's the proportion of people who have passed. So that's just 0.8. So you want this probability that this variable, which is proportion, is bigger than 0.8, which is same as the probability 1 minus the probability that p hat is less than 0.8. Well, let me draw, it will be clearer.
Less than equal to 0.8.
Wait. Yeah. Since it's a continuous, you don't really need to put equal. Less than equal is all same. So this is the probability. This is something like this. Centered at 0.7. This is p hat. Somewhere here is 0.8. You want the probability that At least 80. I should have said, did I say it? At least 80. In your sample have passed. So
Sir,
80.
the mean is 0.7.
Huh? Mean is 0.7.
Sir, that's the mean or it's P?
Well, in the normal distribution, peak is same as the mean. The peak happens at the mean for the normal distribution. So you want the probability.
So P.
So you want the probability of all these things, that in your sample, the proportion of people who have passed is more than 80. So you want this area. But in the calculators which are given, or in the chart you are given, you are told how to compute this number, this area. So that's equal because it's a probability graph. This area, this red area, is just 1 minus this blue area, which is the probability of p hat being less than 0.8. Right? It's very clear from the graph. This is 0.8. The area for the graph which is less than 0.8 is all the probability which is there for this variable to be less than 0.8. But you need this one. So, but this is equal to this. Now you can compute this. And how can you compute it? Well, you can look at your chart, or like me, it's easier to just do it online. You can do it in many ways. For example, I can do it directly by, I have a mean of 0.7 and a standard deviation of 0.0547. And I want the variable to be less than 0.8 and compute the probability. This is the cumulative probability, the total area. So that's 0.966. So my desired probability is 1 minus 0.966, which is equal to 0.034 or something. If you want to do it using the standard normal, then this probability, let's say this one, is that the standard normal variable is less than 0.8 minus, using the formula which we had over here, this relation. Take the variable value if you want to compute the standard variable. This is called the Z value, Z score. It's also written in the book. Minus the mean divided by the standard deviation. So 0.8 minus 0.7 divided by 0.054, which is equal to what? 0.8 minus 0.7, 0.1 divided by 0.054. So probability of Z being less than 1.852. And you can look in the chart but I'm just again gonna look, I'm thinking of it as my chart. For the standard normal, you have a 0 here, standard deviation 1, and I have to put in this 5, 2, which is same as which I got before. I got 0.966. This time I got 0.968 because of rounding errors. Same as before. So any question?
Sir, so what's the final answer? 0.966 or 0.034?
This one, because you wanted the probability that the proportion is more than 0.8, that at least 80 students have passed in your sample.
And sir, the formula of calculating standard deviation is under root p into 1 minus p divided by under root n.
Yeah, for the proportions. For the
If
proportions.
the standard deviation is not given for the population. Otherwise, it's just simply under root n.
No, 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 no. If the standard deviation, this formula, you don't need the standard deviation for the population, because in the population, proportion is just a number. There's no standard deviation for that, right? And you can talk about it's a binary variable, and you're not computing the standard deviation of this binary number. You have just a p proportion in the population, and using that proportion you can compute what would be the standard deviation of the proportion of the samples. Samples are going to give, the sample proportion is going to become a random variable. It will have a standard deviation which would be computed like this. Now there is another statistic which you can talk about. It's called the sample variance. Now I have some data. So like in my example, which I was doing on R, I had this data up to 60, equally probable. And I was picking samples, let's say of size 4. Maybe I get these numbers, and by chance I was doing it with replacement because I'm thinking of them as an infinite and a very big population. So each one of them has a chance of coming again and again. Maybe I get, let's say this ones. Just by chance. So this data, this sample is more distributed, is more varied. Its mean is a mean of these two things will not match. They don't have to match because it's a random variable, but the sample variance, which is just this number, is written as S square. It's just the variance as we had written before, but not computed using any probability distribution. It's just whatever the numbers you have in sample, you compute their mean, and you then give a measure that how far they are spread around their own mean. So this is a measure. Usually you divide by the number of elements you have, like here I had 4. But when you're computing the sample variance, you divide by 1 over n minus 1. If your samples are big enough, it doesn't really matter much. You're dividing by n or n minus 1. Well, it depends, depending on what number you get here. But it's better to divide by n minus 1 instead of n, and it will become clear in a moment that why is that so. So clearly this, if you compute this for this data, that's going to be different. This is more spread out compared to this. And both have a chance to come up. So sample variance is a random number. And it turns out that it is also an unbiased statistic. What does that mean? By definition, that means that if I compute the expectation value of the variance, this variance is random variable, so it will have a distribution. It turns out its distribution is not normal. It's something else. But whatever this distribution is, you can compute according to that distribution that what is the average value of the sample variance. So what is this? This is the average or expectation or mean of the sample variance. And this is equal to the variance. Variance is the square of the standard deviation of the original population. So that's a nice thing to know. And you can also prove that the variance of the sample variance, since it's a random variable, you can compute its own variance. It's this, or standard deviation of the sample variance is it turns out that the probability distribution for the sample variance is not very simple, and it doesn't take any universal form. It depends on what is the distribution of the original population. If the population is normally distributed, which actually is the case in many applications, is the most common distribution you find in nature, then you can say what would be the probability distribution of the sample variance. And the result says that the sample variance, if you multiply it with n-1 divided by sigma square, where this is the standard deviation of, or the variance, sigma square is the variance of the population. This is exactly equal to what they call the chi-square variable, chi-square distribution of n-1 variable. We don't have to go into the this terminology that what does it mean, chi-square of the n-1 variable. All we need to know is that for each index over here, like if you're picking a sample of size 10, then it would be chi-square of the 9. And if you're picking a sample of 8, it would be chi-square of the 7. And each one of them has a certain distribution. They look very strange. They don't look like nice. They're not as uniformly distributed as the normal distribution. They are actually skewed. They are concentrated on one side or the other. But again, you have tables available for them, and you have calculators available for them. And all you need to do is compute that which chi-square variable with which index you're dealing with, and then the table can do the job for you. Again, the ideas which are used are exactly the same. So for example, if this is your chi-square distribution, by the way, it's all, since these, I'm doing the distribution for the variance. Variance is a positive number. You are squaring something, it always comes out to be positive. So all the probability is distributed between 0 and infinity. So suppose if it looks like this, the ideas, it doesn't look like normal, but the ideas are same. Like if you want to compute that the variance would be between these two values, you still have to, taking this distribution, you have to compute this area. If you want to compute that the variance is more than b, you can still use this, that it would be same as 1 minus the probability that the distribution is less than b. So all those ideas, they still apply because it's still a curve and the probability is just the area under it. It's just that the curve's shape is different. So your calculator does the job for you of computing these areas. You just have to know that what's happening. We can do an example of this. So suppose you have a population, and let me pick a example. So suppose this is an example from the book. So you are doing quality control this time, but your problem is slightly different. It's related to variance. You are making some electrical components and whose resistance has a certain value. But since it's going to be used in some precise instruments, and it's going to be dangerous if the value of the resistance is not exactly same. You are given some exact value of the resistance, let's say omega. But since you cannot make everything same, so you do expect some some deviation around this central value of resistance. So you have done make your process and made sure that the standard deviation is within 3.6. Standard deviation is 3.6. It's not more than that. It's just this. That's what your process is. That standard deviation resistance is 3.6 ohms, let's say. And you want to control this number. You want to have an idea about this, that this should stay as the same. It's not only the mean value which you want to stay same. You do not want the components of very high resistance to be going into market, because even one of them can screw your reputation if it malfunctions and burns some equipment somewhere. So you want that there's not much difference between these components you are making. So what would you do? You pick up, you know that your sample size. So suppose you pick, and you're doing quality control by randomly picking from each shipment. You pick n component, each shipment you are sending out. So your population variance is this, and you want that your sample variance to be within some number So S square is the population variance. And you want this population variance to be restricted within some value. You know that it will have a certain it will have a distribution, but you want to get an idea that what is the probability that it will be within a certain tolerable level. So this would be, you can use here the chi-square distribution, probability distribution, to compute these probabilities. Since we are running out of time, so what I'm going to do, I'm going to stop it here and I'm going to complete this problem. I'm going to upload a tutorial. You don't have to be present in the tutorial. I'll just record it and upload. I'll complete this problem and I'll do some more problems over there so that things are clear, and put in an introduction of SPSS there as well. So let me stop here and I'll complete this and some more problems in a tutorial I'll upload tonight, and I'll also upload a homework tonight. So let me stop here.